So welcome to the next lecture of selected topics in graph theory. Today we'll be speaking about the concept of chi-boundedness, which is sort of a extension of whatever we were doing last week, whatever Marcin was doing last week. Marcin was speaking about perfect graphs, and chi-boundedness is sort of a relaxation of this concept that leads to really nice graph theoretical proofs. So just a reminder of what was going on the last time. Perfectness and chi-boundedness as well is about understanding the relation between two important parameters in graphs. One is chi of a graph, the chromatic number of a graph. So this is the minimum number of colors that you need to properly color a graph, where proper coloring is a coloring where every pair of adjacent vertices receive different colors. The other parameter is the click number of a graph, which is just the maximum size of a click in a graph, a set of vertices that are pairwise adjacent. So clearly, if I have a set of pairwise adjacent vertices, a click, then each of these vertices in any proper coloring needs to receive a different color. So you have a trivial inequality between chi and omega. The chromatic number must be at least the click number in the graph, right? So now the notion of perfectness was about studying where you have equality between these two terms, and really having equality on the level of the whole graph doesn't really make sense, because you can always somehow obfuscate the structure of a graph by adding a huge click to it, and therefore like pumping both the click number and the chromatic number up to the size of this click. So the definition was a little bit more nuanced, in a sense that a graph is perfect if and only if the chromatic number is equal to the click number for every induced subgraph of G. And it turns out that this definition leads to a very, on one hand, rich, on the other hand, very well structured class of so-called perfect graphs. There was a lot of work on this, and in particular, this work culminated around 10 or 20 years ago with the proof of so-called strong perfect graph theorem that exactly characterizes when a graph is perfect. This was previously called the Birch conjecture, as far as I remember. And it turns out that the graph is perfect if and only if it doesn't contain any of two possible obstacles for this. So one obstacle is a so-called odd hole. So this is an induced cycle of length that is odd. So for instance, a cycle on 7 vertices, it has click number 2, but it has chromatic number 3. So this is not a perfect graph. And if you contain an odd hole, you also are not perfect, because of this closure of the definition under induced subgraphs. So this is one possible obstacle. The second possible obstacle is an odd antihole, which is just the complement of an odd hole. And it turns out that not having these two obstacles is equivalent to being perfect. So this is one important result about perfect graphs. But from this result, you can easily see that it implies that perfect graphs are closed under complementation. Well, you do not have an odd hole and an odd antihole if and only if your complement doesn't contain, because odd holes and odd antiholes are closed under complementation. Like they complement each other, which means that perfect graphs are closed under complementation. Yeah, a complement of a perfect graph is perfect, and this is a fairly non-trivial and quite surprising at first glance statement. The proof is not hard; it's sometimes called the weak perfect graph theorem, and as far as I understand, we have seen the proof during the last lecture. Good. So these are the two main things about perfect graphs, but as already actually was discussed before the lecture, this perfectness is actually quite a strong condition, and you could think about conditions that are relaxing the notion of perfectness, where we don't really require full equality everywhere of chi and omega. And maybe this relaxed notion would give you something meaningful for broader classes of graphs than just perfect graphs. Yeah? And indeed, this notion exists. It's called chi-boundedness, and here is the definition. Let me look at a graph class, like a possibly infinite set of graphs, and we will focus on hereditary classes of graphs. So these are classes that are closed under induced subgraphs. Yeah, and this the definition makes sense if you don't assume this, but it makes sense to focus on hereditary graph classes because of the same reasons as we as we close the definition under induced subgraphs with perfectness. So let's assume this in the definition. So a class is called chi-bounded if for every graph in my class, for every graph G from my class, the chromatic number is bounded maybe not equal to the it's not maybe equal to the click number, but is bounded by some fixed function of the click number. So in other words, there exists some function f such that the chromatic number is bounded by this function applied to the click number. So maybe the chromatic number is not at most omega, but it's at most say omega squared or 2 to the omega. Yeah, so there's a functional relation between the click number and the chromatic. So this notion of chi-boundedness, it was introduced, I think, in 85 or 86 by Anders Jalfas. And since the introduction, it turned out that it is a really nice notion. A lot of classes of graphs that are not necessarily perfect, but they have very nice structure, they are actually chi-bounded. And studying which classes are chi-bounded and what are the best possible this chi-binding functions f, for them, this is a really thriving part of graph theory nowadays, and there is a lot of really cool work around here. So I want to give you an introduction into this area. One interesting historical note, actually, this paper of Jalfas that introduced this notion was published in Fundamenta Mathematica, which is a Polish journal. It was actually presented at some conference somewhere in Poland, a graph theory article. Good. So let's see some trivial examples and trivial non-examples of this concept. Once we get over them, we will see some non-trivial examples and some ideas of how you prove that actually some class of graphs is chi-bounded. So let's see some trivial examples. Okay, so clearly every class of perfect graphs is chi-bounded, right? Because you always have equality between chi and omega, so you can just have the function, the chi-bounding function, to be the identity function, right? So this is on one hand. On the other hand, whenever you have in your class of graphs, you have a uniformly bounded chromatic number. For instance, the chromatic number of your graph is always bounded by some constant c. You are also chi-bounded, right? Because then you take the function being constantly equal to this constant, right? So for example, planar graphs or graphs of bounded maximum degree or graphs of bounded tree width and so on and so on, they are all chi-bounded for trivial reasons, yeah? Because just chi is uniformly bounded. Good. So in order to make sure that we actually work with a notion that is in any way interesting mathematically, we need to have also a trivial non-example. So let's see why all graphs are not chi-bounded. So in other words, we would like to prove that in all graphs there cannot be a single function that bounds the chromatic number in terms of the click number, and this we will do in a moment. However, maybe now after putting this definition on the table, are there any questions? And if not, maybe you can put a +1 in the chat so that I am happy that the definition is clear for all of you. Okay, I see a wave of +1s, so I guess that everything is clear by now. Okay, so we would like to prove that the class of all graphs is not chi-bounded. And more precisely, we'll prove the following clean statement, saying that there exist triangle-free graphs, so a graphs without clicks of size 3, that have arbitrarily large chromatic number. Yeah, and triangle-free graphs. This means that omega of a graph is at most 2, right? Because there are no cliques of size 3. So we will see that there exists graphs with omega bounded uniformly by 2, where the chromatic number is arbitrarily high. So there cannot be any function that bounds the chromatic number in terms of the clique number. So the proof will be probabilistic. Actually, we'll give 2 proofs. One of them here, one of them during the tutorials. The one during the tutorials will be deterministic. The one that is given here will be an easy probabilistic argument. So essentially, I will sample a graph like that and prove that with high probability, it has good properties. So let's fix some n, say large, let's say at least 1000. I will not actually think about this 1000 large enough. And let me pick some probability p. The probability that I pick is actually equal to 1 over n to 2/3. Yes. So this is my probability, and now I sample a graph, a random graph from the Erdős-Rényi model. So I put n vertices on the table, and for every pair of vertices, uniformly and independently at random, I toss a biased coin, and with probability p, I put an edge there, and with probability 1 minus p, I put a non-edge there. Yeah. So this is my graph, and now I would like to analyze for this particular probability what are the properties of this graph that we have. In particular, how many triangles are there in this graph, and what is the chromatic number with good probability. Okay, so let's first look at triangles, and this graph will actually contain triangles because, well, for any triple of vertices, there's quite a good probability that there exists 3 edges between them. So more precisely, if I have 3 vertices from my vertex v fixed, what is the probability that there is a triangle between them? Well, each of those 3 edges needs to simultaneously appear, and they appear independently. So the probability that there is a triangle is like p to the power 3. So 1 over 2/3 the power 3. So 1 over n squared. Right. So every single triangle appears with this probability. So the expected number of triangles that I see in my graph is, well, there are n choose 3 pairs in total. Each of them becomes a triangle with probability 1 over n squared. So now n choose 3 is at most n cube over 6. So I've got something like this. So the expected number of triangles is n over 6. So in general, in a graph, there can be a cubic number of triangles. But because our graph is sparse, we have a low probability of the existence of an edge. The number of triangles will be actually smaller than n in expectation. So now you can apply Markov's inequality because the expected number of triangles is like n over 6. The probability that the number of triangles will exceed 3 times the expected value, so exceed n over 2, is upper bounded by 1 over 3. So this is Markov's inequality. Good. So we already see that maybe our graph has triangles, but with high probability, it will contain only few triangles. And this is what we will use later. Okay, so now these were triangles that we understand already. So now let's think about the chromatic number. And the chromatic number, we want to think about the chromatic number as covering your graph with independence. So let's pick a particular subset of vertices, A, of size n to 5 over 6. Imagine that this is an integer. We can assume that. And let's bound the probability that this set becomes independent. Yeah, that we have a large independent set as large as n to 5 over 6. So what is the probability that it is independent? Well, each of those k choose 2, where k is this n to 5 over 6 pairs of vertices, must become a non-edge in our sampling, and each of them becomes a non-edge with probability 1 over 1 minus 1 over n to 2/3, right? So now k choose 2, this is k times k minus 1 over 2. I want to bound it from above, so let me just have this k minus 1 because n is large. I can bounded by k squared over 3 in the exponent like this. So now k square, what is this? K is n to 5 over 6, so k squared over 3, this is n to 5 over 3, well, over 3, like here. Yeah, so this is this inequality. So now in the last step, this is the usual trick that you do when doing this kind of estimations. You use the inequality that 1 minus x is upper bounded by e power minus x. So now if this is my x, then I can bound this by e power minus 1 over n to 2/3 times n to 5 over 3 divided by 3. This cancels out, and I get e to power n minus 3. Good. So the probability that a fixed set of size n to 5 over 6 becomes independent is really, really, really small. Yes, it is exponentially small. So with good probability for every set of size n over 5 over 6, for every fixed set, this set doesn't become independent. So what is then the total probability that I do not contain any large independent set? So probability that there is no independent set of size k, where we recall that k is n to 5 over 6. Right, so what is this probability? Well, by union bound, I can say that this is at least 1 minus, and each of those n choose k sets, potential sets that can become independent, becomes independent with this small probability. Right, so this is union bound. So this is at least 1 minus n to k. Yes, and I now bound the n choose k by n power k, which is n power n to 5 over 6. And now this probability that a set is independent is exponential. So now observe that this term is actually asymptotically smaller than this term, yeah, because this is something like e power n to 5 over 6 log n, while this is e power n minus n roughly, right? So actually this, with n going to infinity, this converges to 0, yeah, because this term, the exponential term, actually wins, right? So for large enough n, this will be, say, larger than 2 over 3. Good. So we see already that our graph with large probability, larger than 2 over 3, will contain less than n-half vertices, n-half triangles. And with probability at least 2 over 3, it will contain no independent set of size that large, n to 5 over 6. Good. So these are actually two very good properties for us. Yeah. And because you've got 2/3 here, 2/3 here, by just union bound, you see that both of these conditions hold simultaneously with probability at least 1/3. Yeah, because they need to overlap on a subset of the probabilistic space of with measure 1 over 3. Good. So assume then that both of these conditions hold, and let me call this condition that both of them hold by star. So now my graph still needs to contain some triangles, few of them, but still contains. So let me modify my graph. So let G prime be the original graph G that I sampled, but let me look at every triangle and arbitrarily delete one vertex from this triangle for each of the triangles. So how many vertices I deleted? Well, if my star holds, yes, then there are less than n-half triangles. So I deleted less than n-half vertices in this way. So if star holds, then in my graph G prime, I will still see more than n-half vertices, but the independence number of the graph, the maximum size of an independent set, alpha of G prime, will still be smaller than n over n power 5 over 6, right? Because in the whole graph G, there were no larger independent sets. So in the subgraph in particular, there are no, in this subgraph, there are no large independent sets. Okay, but if I have a graph with large number of vertices, but only small independent sets, yeah, then the chromatic number must be large, yeah, because the chromatic number is at least the total number of vertices divided by the larger size of the independent set, because a chromatic number is a partition into independent sets. I need at least as many colors as the number of vertices divided by the larger size of an independent set, right? And now this is n over 2 linear in ny, while alpha is like n over 5 to 5 over 6. So we see that the chromatic number is at least n to 1 over 6 divided by 2. Yeah. And this concludes the proof, because now our graph G prime, because we explicitly deleted all the triangles, is triangle free, while its chromatic number is lower bounded by a function of good. It is actually a very common trick how to lower bound a chromatic number. You make a graph with no large independent sets and many vertices. This is a usual trick in probabilistic graph theory, how to make a lower bound on the chromatic. Good. So this was this proof that there exists triangle-free graphs with arbitrary large chromatic number. Maybe some questions, and otherwise, please put +1s in the chat if you are happy with this proof. Okay, I've seen some +1s, but not too many of them. Maybe some questions, some doubts. Okay, let's just continue. I think that it was clear enough. Good. So just a few remarks about this. First of all, this is a classic argument of Eidos. The classic argument of Eidos actually proves a little bit more. Instead of just excluding triangles, you can exclude induced cycles of length at most L. So produce a graph with so-called girth, at least something, with no cycle shorter than L. The proof essentially goes the same way. You just need to adjust the probability of the existence of an edge and be more careful about estimating the number of cycles that you get in the graph. So this is one thing. Second, for the particular case of triangle-free graphs, there are known deterministic constructions of such graphs. They're not very hard. We will see one during the tutorials due to Michelski. This is an old construction that is actually very nice. And good. So this was this proof. So now that we understand that chi-boundedness is a non-trivial notion, we can give some interesting examples of chi-bounded classes. And let me just repeat that at least for me, the intuition is that chi-boundedness is not really an end goal of what you are doing in structural graph theory, but somehow it is an indicator that a certain class of graphs has a good structure, has good structural properties. So it is good for studying dense graphs, possibly dense graphs, because for sparse graphs, usually they have bounded chromatic numbers, so the chi-bounded trivially. But whenever you have a class of possibly dense graphs and you expect that there are some good structural properties there, you might ask yourself a question: is this class chi-bounded? And studying chi-boundedness can expose those good structural properties and therefore give you a good understanding of the class itself. So this is why we are interested in this notion. And main sources of examples of chi-bounded classes that we study are the following. First of all, as usual in structural graph theory, we are looking at H-free graphs. So we fix some small graph H and look at graphs that are so-called H-free, so do not contain H as an induced subgraph. And then you can ask for what graphs H you are chi-bounded at, and how you can characterize subgraphs H, or maybe pairs of graphs H1 and H2, and play with this. Another setting where chi-boundedness pops up naturally is geometric graph classes. So intersection graphs of somehow well-behaved geometric objects. We will see this in a moment. So these are two natural sources of examples. So let's look at example number one. This will be actually about intersection graphs of well-behaved geometric objects, namely circular arc graphs. So one class that you have probably already seen before during the last lecture, I hope so at least, are so-called interval graphs. So interval graphs are intersection graphs of intervals on the line. So a graph is an interval graph if you can draw intervals on a line, one in a one-to-one correspondence to the vertices of your graph, in such a way that two vertices are adjacent in your graph if and only the corresponding two intervals intersect. So for example, the interval graph that would correspond to this interval model would be a graph where you have here an edge and here an edge because these two intersect, and here an edge, here these two also intersect, and this one and this one. These two intersect, this and this, this and this. I hope that I did not miss any of the edges. Yeah, so this is an interval graph is a one that has this kind of an intersection model. And then, of course, we have chosen here intervals on a line, but you can choose any geometric object in any topological space that you like, and think about intersection graphs there. Yeah. So, for example, one natural generalization of interval graphs are so-called circular arc graphs, and these are simply intersection graphs of arcs on a circle. So you draw a circle here depicted in, I hope, now violet or pink, and then every vertex needs to be modeled by an arc on the circle. And similar as before, two vertices are adjacent if and only if they do intersect on the circle. So interval graphs, I hope that you proved or will prove during the tutorials that they are perfect. There is a very easy sweeping argument showing that. However, circular arc graphs, they are not necessarily perfect. And the very simple reason for this is that any cycle, including the ones of odd length, is a circular arc graph, because you can simply just draw those arcs like that and model any length you like. Yeah, in particular odd one. So odd cycles are also circular. But now I want to prove that this class is actually chi-bounded. The chi of a circular arc graph is bounded by twice the clique number. And the argument is actually very simple. So yeah, this is the whole argument. Let me take a circular arc graph. So here, let me copy it, and let me pick any point on the circle. Let's say this point, call it x. So now the intervals on this in this intersection model, they can be partitioned into those that contain the set x and those that do not. Yeah, so let k be those guys that contain this this point x, and the rest is the rest. So first of all, observe that k, that the vertices whose intervals contain the point x, they form a clique in the graph. Well, because they pairwise intersect at the point x. Yeah. So in particular, this means that the size of this clique is bounded by the omega of the graph. Yeah, because this is the clique number. On the other hand, observe that if you removed the vertices of k from your graph, you would get an interval graph. Yeah, because now you can sort of unwrap this circle into a line and just get an interval model of your graph. Yeah, just break this circle here and straighten the circle. Yeah, so this means that if g minus k is an interval graph and clearly the omega of g minus k is upper bound by the omega of g, yes, then this means that I need omega of g colors to color the remaining vertex, to color g minus k. So how many colors do I need to color the whole graph? Well, it suffices to use omega plus omega colors. I put every vertex of K into a separate color. It will be the only vertex of this color. And then for the remaining vertices of G minus K, I use the omega colors that I get from a coloring of an interval. Yeah. So here, in some sense, by a easy modification of your graph, we reduced the question about chi-boundedness to actually invoking perfectness of some graph that we already understand. Good. So some note about this. This was actually, I think, the first example of JFH that he was giving in his paper, and the actual tight bound for circular R graph is like 3/2 times omega. Yeah, so you can squeeze a little bit more from this argument if you are more careful about picking this point X on the circle. Good. Is this clear? Are there any questions? And if there are no questions, then please put a +1 if you understand this argument. Okay, I see a fair number of +1, so let's continue. Yeah, so this was the first very simple example, but the reasonings proving high-boundedness get more complicated with time. Good, so let's make another simple example, this time Clawfree graphs. So this will be about H3 graphs from some small graph H, and the graph H that we will be looking at is the so-called claw. So a claw is simply a star with three leaves. Yeah, so K1 3. Here is a claw. And as the name suggests, a graph G is claw-free if and only if it doesn't contain a claw as an induced. So I now claim that claw-free graphs are actually observed that claw-free graphs are not perfect because a cycle is claw-free, an odd cycle is claw-free in particular. But I claim that they are chi-bounded. I claim that the chromatic number of a claw-free graph is bounded by this funny function, which you can recognize as the Ramsey number of omega and 3. Yes. So the Ramsey number being that in any bicolored click, or rather in any graph on at least this number of vertices, you either see an independent set of size 3 or a click of size omega. Yeah, and the bound on this Ramsey number can be proven like this using standard bound. So this is actually a polynomial in omega. Good. So what we will actually prove is a stronger statement than just bounding the chromatic number. We'll actually prove that the maximum degree is strictly smaller than this number K, this Ramsey number. And obviously, if I prove that the maximum degree is strictly smaller than K, then from this assertion, this implies that the chromatic number is bounded by at most the maximum degree +1, because I can just trivially color the graph with delta +1 colors. And if delta is strictly smaller than K, then this means that this is smaller or equal than K. So this will be the proof. We'll actually prove that the graph has small degree, small in terms of omega. Okay, so suppose otherwise. Suppose that there exists a vertex U in your graph that has large degree, that has degree K, this Ramsey number. Okay, so let's look at its neighbors. There are K of them. Would it be possible that there was an anti-triangle among the neighbors, that there were 3 neighbors that are pairwise non-adjacent? Well, no, because this would be a claw, right? With U being the center and these 3 guys being dependents, being the leaves. So this would be an induced claw, so this is not possible. So there is no independent set of size 3 in the neighborhood of U. Okay, so if there is no independent set of size 3 in the neighborhood of U, this means that there is a large clique, right? I see here omega of G by Ramsey's theorem, vertices that are pairwise adjacent. Okay, I will not draw all of them. But now I see a clique of size omega of G in the neighborhood. So if I now add U to this clique, I see a clique of size omega of G +1 in the graph. But wait, omega of g was the largest size of a click in my graph, so this is a contradiction, right? Good. So this is the whole proof. Just by Ramsey's theorem, if I have a bounded click number in a Clawfree graph, I have also a bounded degree. Okay, so observe that actually there was no magic in the number 3 in this proof. Actually, this works for H3 graphs where H is like K1T, so a star with T leaves for any fixed T. They are also chi-bounded. Good. So this was the question of Clawfree graphs. So these were two easy examples. Any questions about the Clawfree graph example? Any plus ones, maybe? Please put a plus one if you are happy with whatever happened so far. Okay, I see plus ones. Let's just then continue. Okay, so now we, during the remainder of the lecture, we will actually give two non-trivial examples of chi-bounded classes. First example will be so-called rectangle intersection graphs. So this is a geometric example. So a rectangle intersection graph is a graph that has an intersection model of consisting of axis parallel rectangles in the plane. So for every vertex of your graph, there should be a rectangle in the plane. Yeah, so here are those rectangles. Yes, and you put an edge between two rectangles if and only if they intersect. And by intersect, I mean that the rectangles are actually solid inside. So for instance, if one is contained in the other, like these two, they are also connected by an edge. So the intersection graph of those would probably look like this. Yep. So this is an intersection graph of axis parallel rectangles in the plane, and it is easy to see that this graph class is not perfect. For instance, you already see here. Oh wait, actually, I did not manage to get an odd hole in this particular intersection graph, but it is very easy to arrange an odd number of rectangles in the plane into a sort of a necklace where they intersect in this cycle pattern. Yes, where the length of the cycle is odd. So this is not a perfect graph class, but we will prove now that this graph class is chi-bounded. So we will prove that the chromatic number of a rectangular intersection graph is at most 8 times the click number square. Yeah? So now it will not be linear in omega, but it will be quadratic. Okay, we need some preparation for this result. We will need a few auxiliary results about comparability graphs. So what is a comparability graph? A comparability graph is a graph that can be understood as a poset through a poset. So there is a comparability graph is a graph where you can find a partially ordered set on a partial order on the vertices of your graph, such that you have an edge between two vertices if and only if these two vertices are comparable in the poset. Yeah. So for example, if here is a poset, this is the Hasse diagram of the poset. So there should be also order induced by transitivity here. What would be the comparability graph induced by this poset? Well, you put all the edges that are there. These are just the basic comparability relation. Yes. Plus, you also have this transitive edges that are implied by the order. Yeah. So this would be the comparability graph with this poset being the model for this graph. Yeah. So this is a comparability graph, and not all graphs can be defined in this way. A co-comparability graph is just a complement of a comparability graph. So in a sense, a co-comparability graph is a graph where you can model the edge relation by the incomparability relation in a poset. while a comparability graph is a graph where you can model the edge relation by the comparability relation. Good. So these are two interesting classes of graphs. And let's think about what does it mean to color a comparability graph or to find a click in a comparability graph or a co-comparability graph. So say that G is a comparability graph and G complement is a co-comparability graph. So a click in a comparability graph is the same as the chain in a poset. Yeah, so a set of pairwise comparable elements. Yeah, so a chain looking like this. Of pairwise on which the order induces a total order. And then in the co-comparability graph, this is an independent set. Yeah. On the other hand, if I think about an independent set in a comparability graph, this is a set of pairwise non-incomparable elements, so an anti-chain in the poset, in this poset that models the graph. And in the co-comparability graph, this is a click. Right. So now, if you know a little bit about combinatorics, you probably have seen two duality theorems about posets, and now we will be going to reinterpret them. One is Dilworth theorem, and second is Mirsky theorem about the duality of chains and anti-chains in a poset. So Dilworth theorem, this is the more classical one out of these two. Just says that if I have a poset and I would like to partition this poset into as few chains as possible, yes, then clearly if I see some anti-chain, yes, then each of these elements of the anti-chain must be in a different chain in our partition, right? So the maximum size of an anti-chain in my poset is a lower bound on how many chains I need to have in order to partition my graph. Yeah, and the Dilworth theorem says that actually in here we've got equality. So the minimum number of chains into which you can partition a poset is equal to the maximum size of an anti-chain that you can find in this poset. So observe now that these guys, the chains into which I partition the graph, well, chains are independent sets in a co-comparability graph, while anti-chains are clicks in a co-comparability graph. Yeah, so partitioning into chains is proper coloring of a co-comparability graph, while maximum size of an anti-chain is the click number of a co-comparability graph. So Dilworth theorem in graph theoretic terms says exactly the following, that co-comparability graphs are perfect. So this is just a restatement of Dilworth theorem in terms of co-comparability graphs. And there's a second theorem that gives you the second duality, which is usually attributed to Mirsky, that says that the minimum number of anti-chains into which you can partition your poset. Yeah, so now I'm partitioning the poset like this into anti-chains. Yes, is equal to the maximum size of a chain that you can find in your poset. Yes, and again, partitioning into anti-chains, this is coloring a comparability graph, and size of a chain in a poset is the same as the click size in the comparability graph. So the theorem of Mirsky can be rephrased in graph theoretic terms as saying that simply comparability graphs are perfect. Good. So these are two classic results about posets that we will use, this perfectness of those graph classes. However, observe that we have already seen during the last lecture that perfect graphs are close under complementation. So comparability graphs are perfect if and only if co-comparability graphs are perfect, right? So this means that the stuff that we used, that we proved during the last lecture, means that Dilworth's theorem is actually equivalent to Mirsky's theorem. Yeah, because in order to prove that, say, co-comparability graphs are perfect, it only requires to prove that comparability graphs are perfect and apply the complementation. So we will prove actually Mirsky's theorem, and then you can, because this is the easier one, and then you can get the Dilworth's theorem as a corollary of this. Okay, so Mirsky's theorem is actually really simple. This is your poset. I will do induction on, say, the size of the poset. I would like to partition my poset into as many anti-chains as the largest size of a chain in this poset. So let me look at the maximal elements of the poset. Yeah, so the ones that are not upper bound by anything other. Yeah, so maximal elements. Clearly, they form an anti-chain, right? Because if there was any comparability relation between one of them would not be a maximal one. Yeah? So they form an anti-chain. So this is one observation. And second, if this is my anti-chain I, if I remove I from my poset and I look at the rest, right, then clearly the maximum length of a chain decreases, because every maximum length chain in this poset must contain a maximal element, yes, as the topmost one, right? So yeah, we can then extract this anti-chain of maximal elements. The maximum chain length decreases, then again extract the maximal elements, again the maximum chain length decreases, and so on and so on. How many anti-chains we have extracted in this way? Well, as many as the maximum chain length, right? Because every time we are doing this, the maximum chain length decreases. Yeah. So we can also phrase this through induction. So Mirsky theorem is actually very easy to prove, and then Dilworth follows by complementation. Good. Any questions about the comparability graphs, co-comparability graphs, and this proof of Mirsky theorem? Okay, no questions. Then let me go back to the rectangle intersection graphs. And we will use the results about comparability graphs there as for the for our proof. Good. So let me first introduce a definition. Two rectangles, I will call them piercing or piercing each other if one contains a vertex of the other. So for instance, these two rectangles, they are piercing because this large one contains these two vertices of the other. Well, if they intersect in a sort of a regular way, yeah, one contains the vertex of the other and vice versa. Yeah, so they can piercing in both directions. For instance, these two guys are also piercing because this larger rectangle contains all the four vertices of the other. What are non-piercing rectangles? Well, two of them that are completely disjoint, they are definitely not piercing. But also you can have intersecting rectangles that are not piercing. And this is a situation like this, right? Where these two rectangles are actually intersecting, but they intersect in a way that all the vertices are not contained in the other. Good. So our first goal is to actually color the graph in order to get rid of all this piercing, not really intersections, but really piercing relation. So first observation, a very easy one, is that whenever I have let me just recall what we are trying to do. We are having this family of rectangles in the plane. Omega is the maximum clique size, so the maximum subset of those rectangles that pairwise intersect. And the goal is to partition my family of rectangles into 8 omega square subfamilies of rectangles that are independent. And independent in this sense means pairwise non-intersecting. Good. So now we are focusing on not really getting pairwise non-intersecting, but at least pairwise non-piercing. So first observation, very simple one, is that whenever I have my any rectangle for my family, there is only a bounded number of other rectangles that contain any of those 4 corners or vertices of this rectangle. So at most, 4 omega minus 1 other rectangles can contain a vertex of A. And the proof is very simple, right? Because for each of those 4 corners, there can be at most omega minus 1 rectangles that contain this particular corner, because they all form a clique because of intersecting at this corner. So for each vertex or corner, these are two synonyms here, of this rectangle, there are at most omega minus 1 other rectangles that contain it. Yeah, so 4 omega minus 1 in total. Okay, so now let me think about this piercing graph on R. So R is my family of rectangles, and now I make a graph where 2 rectangles are considered adjacent in this piercing graph if they pierce each other. Yeah, if one pierces the other. And the claim that I'm now making is that this graph is actually sparse. And this graph has degeneracy at most 8 omega minus 1. I hope that you remember the notion of degeneracy. This was used in the when we were talking about planar graphs. But just to recall, what we want to prove in order to prove this lemma is that whenever I take a subset of my rectangles and I look at the subgraph induced by this subset in this piercing graph, then there is a vertex, so a rectangle, that has degree at most 8 omega minus 1. Yep. So there is a rectangle in this subset of rectangles Q that is in the piercing relation with at most 8 omega minus 1 other rectangles from Q. So this is the notion of degeneracy. The proof is also quite simple. Essentially, it follows from this observation that we had just before. So whenever I've got 2 rectangles that are piercing, say this one and this one, this is say A and this is B, yes. And they pierce each other. So in this piercing graph, they are actually connected by an edge. Let me orient this edge from A to B if actually the vertex of A is contained in B. Well, if they are piercing in both ways, let me orient this edge in any way. So this means that every vertex, so rectangle in our piercing graph, has in degree at most 4 omega minus 1. This is exactly this observation and that we have just made. That every rectangle can be piercing at most 4 omega minus 1 other rectangles, right? So how many edges there are in the induced subgraph of this piercing graph induced by our subfamily Q? Well, let's count in degrees. Yes, every vertex of Q, every rectangle of Q can bring with itself at most 4 omega minus 1 edges that are incoming to this vertex. Yeah, so the total number of edges in this subgraph is at most 4 omega minus 1 times the cardinality of Q. Okay, so what's the average degree in this graph? Well, the total sum of degrees by the handshaking lemma is twice the number of edges. So this is upper bound by 8 omega minus 1 times Q. Yes, and for average, I need to divide by the number of vertices. So divided by Q. So this is equal to 8 omega minus 1. Yeah, so this is a very simple lemma that if you can orient your graph so that the in degree is at most 8 omega minus 4 omega minus 1, then there must be a vertex by the averaging argument. The average degree is at most 8 omega minus 1 in your graph, and therefore there must exist a vertex of degree at most 8 omega minus 1, just by average. Good. So now our graph has degeneracy 8 omega minus 1, and maybe you recall from the planar graphs case that the degeneracy is actually really good for coloring the graph. That means that the chromatic number of a graph is bound by the degeneracy of your graph plus 1. And the argument for this is as follows. So take the whole graph and order it in the following way. Take the whole graph. It has a vertex of degree at most 8 omega minus 1. Put it at the end of the order and remove it from your graph. Again, this subgraph has a vertex of degree 8 omega minus 1. So put it here, and so on and so on. So you get an ordering of vertices with the following property, that every vertex has at most 8 omega minus 1 neighbors to the left. And then you color the vertices greedily from left to the right by assigning to every vertex a color that is not present among its left neighbors. You can use 8 omega minus 1 plus 1 colors because there will be, if you have that many colors, so 8 omega minus 7 colors, there will be always a color free to color your vertex, to color every next vertex. So this is just a recollection of a proof that hopefully was there for when talking about the generality of plane. Good. So the corollary of this is that this piercing graph, so the graph of the piercing relation between the rectangles can be colored with 8 omega minus 7 colors. So let me round it to 8 omega just to have nicer numbers here. So what we have actually achieved now, just recap. We have partitioned our graph, we have partitioned our family of rectangles into at most 8 omega subfamilies, colors, yes, such that within each family, the rectangles are pairwise non-piercing. They may intersect in this funny crossway, but at least they are not piercing within each family, right? So now the idea is that we will focus on each of those families separately and color them, and then take like the union of those colorings by assigning a different palette of colors to each of those families. And the key observation now is that if I look at any subfamily of rectangles that is pairwise non-piercing, then the intersection graph of this family is actually already very, very good. It is a comparability graph. Yeah. So now in order to prove that it is a comparability graph, I need to prove that I need to give you a partial order with the following property that two rectangles are intersecting now if and only if they are comparable in this order. And the order is as follows. So imagine I've got two rectangles, say rectangle A and rectangle B. Yes, they are non-piercing, and I make them comparable and say A smaller than B if they intersect. This is one precondition for them being comparable. And second, I put the one that is actually it should be the other way around, probably. This should be A and this should be B. No, sorry. Yeah. Yeah. This should be B and this should be A. I take the one, the smaller one is the one that is narrower. Yeah. So if they do intersect, because they are non-piercing, they need to intersect in this crossway. So one is like the projection on the x-axis is of one is contained in the other, and then I make the one that is narrower smaller than the one that is wider. Yeah. So this is the definition of my order relation, and in order to prove that it is a partial order, what I need to prove is that this is transitive. Yeah. So this is a non-trivial check that needs to be done. Why is it transitive? Well, let's imagine that A is smaller than B, like on this picture, and the B is smaller than C. So how the C would look like? Well, the C would need to look like this, I guess. Yeah. So now you see from this picture, so let me omit the proof as it can be easily seen here, that if A is smaller than B, so they intersect and in this way, and B is smaller than C, then actually A is also smaller than C. Both A and C also intersect, and A is clearly narrower than C. Good. So this means that this is a partial order on the rectangles from our pairwise non-piercing subfamily, and the two rectangles, they intersect if and only if they are comparable in our order. So this means that the intersection graph within a non-piercing subfamily is already a comparability graph. So in particular, it is a perfect graph. So we are essentially done now. So the wrap up is as follows. So we have partitioned our whole family of rectangles into 8 omega subfamilies that are pairwise non-piercing. Yes. Then each of them induces a comparability graph. And therefore, by Mirsky's theorem, I need at most omega colors to color each of those subfamilies. Well, omega of the subgraph induced by the subfamily, which is upper bound by the omega of the whole graph. So how many colors we need in total? Well, for each of those 8 omega families, we assign a separate palette of colors consisting of 8 of omega colors. So in total, we have 8 omega palettes, each consisting of omega colors. So 8 omega square colors. And this is a very common theme in all the chi-boundedness proofs. You would like to, well, maybe not all, but many of them. You look at the structure of your graph and you try to partition it into pieces that are simpler. And by simpler, we mean, for instance, in this case, they do not have this piercing relation, which gives you a possibility of understanding that they are actually perfect. They are comparability graph in this sense. And therefore, you get a partitioning into simpler pieces, and then you can, using stronger properties of the pieces, you can get more and more structure, eventually getting to a class that says perfect. So this is a very common strategy here. And therefore, because these proofs, they look like that, they really give you some insight into the structure of your class, because on the way you are actually proving some nice decomposition lemmas about graphs from your class. Good. So this was the proof of chi-boundedness of rectangle intersection graphs. Let me give some comments. Okay, maybe before the comments, are there any questions about this proof? And otherwise, if you understand the proof, put a +1 in the chat. Okay, I see some +1s, but not that many of them. Are there any questions? Could I clarify something? Okay, if there are no more questions, then maybe we can move to the next example. But before the next example, let me give you some remarks about this. So first of all, this proof that I gave you is actually much older than the notion of chi-boundedness itself. It was given by Asplund and Grunbaum in actually 1960. And getting anything better than this quadratic dependence was open for 60 years. And it was resolved last year. It was a big open problem. It was resolved last year by Paina, Chalemsuk, and Bajtek-Walczak from Jagiellonian. They gave a new proof that is like omega log omega. This is very tricky, but it's not super hard in a sense. It uses some results from approximation algorithm on rectangle intersection graphs, and the resolution is could be presented within one lecture for sure. So there is exciting new progress here, and I think that getting this down to a linear chi-boundedness bound is an open problem, and people are working on it, as far as I know. Yeah, so then you can also ask how much you can push this result in terms of generality. Actually, this is a delicate thing. So the one natural attempt of generalization is just to think about boxes in 3D instead of boxes in 2D. And it turns out that actually this doesn't work. If you look at axis parallel boxes in 3D, then intersection graphs of those boxes are not chi-bounded. You can make an example of triangle-free graphs. I think triangle-free graphs there that contain arbitrary, that have arbitrary like chromatic number. Another possible generalization is to allow different shapes than just, still in the plane, but allow different shapes than just rectangles. But this also is very short-lived, in the sense that if you look at the intersection graph of segments in the plane, but not necessarily axis parallel, so just draw some segments and make an edge between two segments if they intersect. It was open for quite a long while whether those intersection graphs are chi-bounded, and it turns out that not. There was a paper, I think 10 or 15 years ago, involving a big group of people from Krakow, proving that this graph class is actually not chi-bounded. So this is a limit here in the geometric setting currently. Okay, so these were notes about the notion of chi-boundedness for geometric objects in the plane and model. So the last example, the one that I particularly like, and which also gives a lot of structural understanding of a certain graph class, is one from the original paper of Jaffash, the example of PT3 graphs. So a PT is a path on T vertices. So here is a path on, I think, 8 vertices. So this is P8. Yes. And as usual, a PT3 graph is a graph with no induced path on T vertices. Yeah. So for instance, P4 free graphs, so graphs excluding a path on 4 vertices, they are called co-graphs. And they have very nice structure. In particular, if you know, they have click with 1. There are they admit a certain kind of a very strict decomposition, and in particular they're perfect. And I think that during the tutorials you will prove today that they are perfect. So P4 free graphs are actually very simple, but then you can ask about P5 free graph, P6 free graphs, and there is still quite a lot of structure in PT free graphs, but this is not structure that can be easily described. And the proof of Jaffash about chi-boundedness of PT3 graphs, this gives you a very nice tool for understanding structure in those graph classes. So now we will prove the following bound, that if I've got a PT3 graph, then the chi of G is bounded by t minus 2. I think I need to assume t at least 4. T minus 2 to the power omega of G minus 1. I hope that I did not miss any plus minus ones in those numbers. Yeah, but observe now that all the chi-boundedness proofs that we have done so far were giving a polynomial function. Now, actually, our chi-boundedness will be exponential in omega. Good. So this is what we are going to prove now. So the proof will be on by induction on omega. So we'll do induction on the click number of your graph. Clearly, if omega is equal to 1, or by omega I just mean the omega of G, then the graph is trivial. Yeah, meaning omega equal to 1 means there are no edges, which means the graph is edgeless, so I can use just one color to color it. Yeah, so the base case is trivial. Good. So now we suppose that G is a PT3 graph, and the chromatic number is large. So we are doing by contradiction. Yeah. So suppose that omega is a PT3 graph, and chi is large. Is it larger than this f of omega, which will be a shorthand for this nice function t minus 2 to omega minus 1. And the main point is that this function satisfies this recursive relation that f of omega is equal to f of omega minus 1 times t minus 2. So essentially, we'll give a proof that will blow up the bound by multiplicative factor t minus 2 with every induction step. Okay, so this is a graph with large chi. So without loss of generality, we can assume that G is connected. Why so? Well, because the chromatic number of a disconnected graph is just a maximum of the chromatic number of connected components. So if I've got a graph that is PT3 and has large chi, then one of its connected components must have that large chi. Yeah, so I can just focus on this connected component. So my graph is now connected. So now the idea is to try to greedily construct an induced path of length t using the assumption that the chi is large. And this will be quite tricky. So let me pick any vertex, call it U1. It is here on the left of the graph. And let me try to draw this path as follows. So first of all, let me look at all the neighbors of U1. So here, this vertex is here. Yes, this is the neighborhood of U1. Yeah, and here are everywhere edges. Yeah, so these are all the neighbors, and the rest of the graph are the non-neighbors of U1. So now comes the key observation. Let me look at the subgraph induced by this red box. the subgraph induced by the neighborhood of U1, excluding U1. I claim that the click number in the subgraph is actually strictly smaller than the click number of the whole graph. Why so? Because if I find here any click, say of size 4, yeah, then I can always add U1 to it and get a click of size 5, right? So whatever click I find in the neighborhood of U1, I can add U1 as well and get a click one larger. So this means that in this graph induced by the neighborhood of U1, the click number must decrease. And this is the key point, because now we are doing induction on omega, which means that I can apply my induction assumption to this neighborhood. Yeah, so I can now color this neighborhood of U1 with f of omega minus 1 colors. Yes, I am allowed to, meaning if I want just to color this neighborhood, f of omega minus 1 colors would suffice to color this neighborhood. But I need to color the whole graph, right? So yeah. So now let's look at the connected components of the rest. Let's remove from the graph U1 together with all the neighbors of U1, and then the graph dissolves into several connected components. Here is one, here is another one, here is yet another, and so on. I claim that one of those connected components needs to have large chi, needs to have chi larger than t minus 3 times f of omega minus 1. Recall that f of omega is equal to t minus 2 times f of omega minus 1. Why? Because if chi was smaller or equal than t minus 3 times f of omega minus 1 in each of them, then I could color my whole graph with this many colors. How? Each of those guys, each of those connected components, I color with this many colors. I reuse the colors here. I just take a palette of this many colors and I use this palette to color each of those connected components separately. Then I use f of omega minus 1 other colors to color the neighborhood. Yeah, so this is a separate palette of f of omega minus 1 colors. And then I just need to color U1, so I can reuse any of the colors from here to color U1, and U1 is non-adjacent to those guys, so it's safe to reuse. So if the chi was smaller than this in each of those connected components, then the whole graph G would have chi upper bounded by f of omega. Yeah, because this is t minus 3 times f of omega minus 1 plus this f of omega minus 1 colors for the neighborhood. Yeah. So this means that if my chi of the whole graph was large, this means that there must be some connected component, call it G2, yeah, that still has a large chromatic number, where the chi is larger than t minus 3 times f of omega minus 1. Okay, so let's, because the graph is connected, I can find here a vertex. Maybe I'll remove this. I can find here a vertex U2 that is simultaneously in the neighborhood of U1 and has some neighbors in G2. And I can play this game further. Yeah, I can look at the neighborhood of U2 inside G2. Yes, and again, this neighborhood can be colored using at most f of omega minus 1 colors, which means that if I partition the rest into connected components, there must exist a connected component with chi larger than now t minus 4 times f of omega minus 1. Why? Because if each of them had chi smaller, then I could color this graph G2 with t minus 3 times f of omega minus 1 colors by coloring the connected components using the same palette of this many colors, and then adding additional palette of f of omega minus 1 colors for the neighborhood of U2. And so on and so on. So then I can find U3 somewhere here, and so on and so on. Yeah. So in this way, we can greedily construct a path. And observe that in this argument, actually this argument directly lists a connected component with chi being at least that large. In particular, says there at least a connected component. Yeah. So in particular, it gives us the possibility of continuing this game. Yeah. So more precisely, by U2, I take any neighbor of U1 that is adjacent to G2. Then I find a connected component G3 of G2 minus the neighborhood of U2 that has still large chi, larger than t minus 4 times f of omega minus 1, and I take u3 to be any neighbor adjacent to u2 and g3, and so on and so on, up to the point where I pick ut minus 1, which is any neighbor of ut minus 2 that is adjacent to the next graph. And if you follow these numbers here, this will be a connected component with chi larger than 0, which means non-empty. Yeah. And then at the very last moment, where you have here already ut minus 1, and here you know that there exists some connected component gt minus 1 that is non-empty, you just finish it by adding one more vertex ut here arbitrarily. Okay, so what we have now constructed? We have constructed this path u1, u2 up to ut. And now observe that this is an induced path. Why? Because we started with u1, then we went to u2, which was a neighbor, but then whatever we have further constructed was constructed in a connected component that was the connected component of the graph after the removal of all the neighbors of u1. So in particular, whatever we constructed later was already not connected to u1. And for u2 as well, whatever we constructed after u3 will not be connected to u2, and so on and so on. So at the end of the day, this path u1 up to ut is an induced path on t vertices, an induced pt, and this is a contradiction. Yeah. And this concludes the proof. So this was really tricky because we sort of used the fact, the assumption that the chromatic number is large to guide our process of constructing a path by essentially saying chi must be large, so some connected component must have large chi, so I can proceed into this connected component. Yes, and at every step I'm losing only f of omega minus 1 on the chi, which allows me to proceed for as many steps as I need in order to produce a path on t vertices, eventually reaching a contradiction. Good, so this was a really tricky proof. Are there any questions about this proof? Otherwise, please put a +1 if you understood it. Okay, I see some plus exclamation mark, but I guess that this is just a shift. It doesn't work. Okay, so I see that there are some +1s, sufficiently many. So I hope this proof is understandable. This is a very nice proof template for working with PT3 graphs. A lot of very nice results about PT3 graphs. We will see some of them during the tutorials next week. It can be proved using some juggling with this kind of an argument, where instead of, say, the chromatic number, you take a different measure of complexity of a connected component. For instance, the number of vertices or something like that. We will see it later on during the tutorials. Good, but this gives you a chi-boundedness of the class of PT3 graphs for any fixed t. Okay, so I would like to finish this lecture by rather than going into further results, just discussing some open problems about chi-boundedness, because there is a lot of them. So one thing that I am actually pretty interested personally research is the distinction between chi-boundedness and polynomial chi-boundedness. So a graph is, say, polynomially chi-bounded if it is chi-bounded, and this chi-binding function, this function f, that governs this inequality between chi and omega, can be chosen to be a polynomial function. So in circular R graphs, in the Clawfree graphs, and in the rectangle intersection graph, always this function was polynomial, but in PT3 graphs, not necessarily. So in particular, it is currently open, and this is a big open problem, whether P5-free graphs are actually polynomially chi-bounded. Yes. So our proof that we have just now seen gives you a bound of 3 to the omega minus 1. Yeah. But whether you can improve this to a polynomial bound in omega is a big open problem. In particular, this would imply the Erdős-Hajnal conjecture for P5 free graphs, whatever it is. And this is already by itself a big open problem. So even though this question looks very innocent, it is actually a very deep question. It is believed to be a very deep question. But in general, it would be still consistent with our knowledge if PT3 graphs would be polynomially chi-bounded for every fixed t. Yeah, so we know that they are chi-bounded by an exponential function, but it would be consistent with our knowledge if for every t there was a polynomial bound on the chi-boundedness of PT3 graphs. It is, however, known that the degree of the polynomial must grow with t. This is known. But in general, this is a very curious open problem that we actually do not know of any hereditary class for which we could prove that it is chi-bounded but not polynomial chi-bounded. Actually, we know classes that are exponentially chi-bounded. We do not know whether they are polynomial chi-bounded, but we do not know any graph class where we have a provable distinction. So this is a conjecture that is usually attributed to Louis Espaya. Some people say it's not a conjecture, it's a provocation. But actually, it would be very nice to at least artificially construct such an example. Okay, so these are questions about polynomial chi-boundedness. There are also many other graph classes of dense graphs where you can ask about chi-boundedness relation, like bounded clique with graph, bounded twin with graph, if you know this kind of stuff. So there's a lot of work to be done there. One question about chi-boundedness, so without polynomial flavor, just chi-bounded or not, is the main open problem in this area, which is the so-called Jaffa-Sumner conjecture. So we have already seen that if you exclude a path of any length, pt, then you are chi-bounded, right? This was one of our examples. We have also observed that if you exclude a star of any size, then you are also chi-bounded. Right? So these two examples suggest the following conjecture, that if you exclude any tree, any fixed tree, then you are chi-bounded. And this is actually still open, is Jaffa-Sumner conjecture. There is quite a lot of work on this. In particular, it is known that if you exclude any tree and all its subdivisions and as induced subgraphs, then it is true. This is a result of Scott from the 90s. But the full conjecture still stands open, and many really good people are working on partial progress towards this conjecture. So this is also a very alive topic nowadays. Good. I think that this was everything I wanted to talk about today. I'm very happy that I managed before time this time. Are there any questions at the end of the lecture? Okay, if not, then thanks a lot for today. And I invite you all to the tutorials that will be in half an hour, given my margin about perfectness. Next week, we'll be doing the tutorials from the chi-boundedness, plus we start a new topic, which is expanders. Okay, so thanks a lot.